Question 16 is reminding you about a stationary wave being set up as a superposition of one wave travelling that way and another wave with the same frequency and velocity travelling that way. And what you get is a wave where you get these fixed points, which are the nodes where the amplitude stays at 0, and in between the amplitude just oscillates between positive and negative and back again. And the important thing is that the distance between each node is lambda over 2, where lambda is the wavelength of the original travelling waves going in each direction. So if you remember that, that's going to enable us to work out what's going on here. So it gives us the frequency, which is 1.4 megahertz, and we're talking about radio waves, so in other words electromagnetic waves, so the velocity is, as always, 3 times 10 to the 8 meters per second, as it is for all electromagnetic waves. So we can use those two numbers to find the wavelength. Lambda is equal to c over f, which is 3.00 times 10 to the 8 divided by megahertz, remember, is 10 to the 6, so 1.4 times 10 to the 6. And if you calculate that, that comes to 214 meters, which sounds a lot for a wavelength, but remember we're talking about radio waves here, so that's fine. So that's what lambda equals. So lambda over 2, which is the node spacing, is just half of that, which is 107 meters. So that's the minimum distance between two nodes. So that's the answer, which is A. Question 17 is also about setting up stationary waves, the same as question 16. This time we're doing that by transmitting microwaves along here, and then they're bouncing back off a metal plate and going back the other way, and we're going to get a superposition between the two waves travelling in opposite directions. So again, the important thing is that we're going to get a standing wave. So we're going to get, you know, something like this. And again, the important thing is that the distance between successive nodes is lambda over 2, and likewise, of course, the distance between successive antinodes, which are the maxima in intensity, is also lambda over 2. So we have to look at these things and say which of these statements, A, B, C and D, are compatible with that result. So the first says that the distance between two maxima could be 15 millimeters. Well, it tells us that the wavelength is 30 millimeters. Okay, so lambda is 30 millimeters, which obviously means that lambda over 2 is 15 millimeters. So the distance between two maxima, between two minima, could indeed be 15 millimeters, because that's half a wavelength. So A is possible. B, the distance between two maxima could be 30 millimeters. Well, it could be, because the distance between adjacent maxima is 15, but the distance between this one and this one would therefore be 30. So yeah, that's absolutely fine. The distance between a minimum and a maximum could be 30. That one is not possible, because you can see that the distance between a minimum and a maximum is going to be either a quarter of a wavelength from there to there, or 3/4 of a wavelength, or whatever, but it's not possible for it to be equal to a whole wavelength, and therefore C is the one that's not possible. We can just check out D. The distance between a minimum and a maximum could be 37.5. Yes, it could be, because 37.5 is 1 1/4 wavelengths. So if we think about that, starting from here, one wavelength takes you to there, and then a quarter of a wavelength takes you to there. So that's going from a maximum to a minimum. So yes, that could be possible. So C is the one that isn't. So C is the answer. So question 18 is a diffraction grating question, and the key equation in diffraction grating questions is, on your data sheet, is n lambda is d sine theta, where d is the slit spacing or the line spacing on your diffraction grating, and theta is the angle between the 0 order peak and the nth order peak. And in this case we're talking about the first order peak, so n is equal to 1 in this case, so we can simplify that just to lambda is equal to d sine theta, and therefore d, which is what we're going to need in order to find the number of lines per millimetre, d is equal to lambda over sine theta. So the first thing we need to do is to find theta, and you can see we can do that because we know this distance, the distance between the 0 and first order maxima, and we also know this distance, which is the distance between the screen and the grating. So if we know that and that, we can say that tan theta, because this angle is theta, so the tangent of that angle is equal to 0.30 over 1.50, which is 0.20, and therefore theta is the inverse tangent of 0.2, which is 11.31 degrees. Okay, so we can just very easily use trigonometry to figure out what theta is. So that's equal to, now it tells us the wavelength in the question, 6.5 times 10 to the minus 7 meters. So that's 6.5 times 10 to the minus 7 divided by the sine of 11.31 degrees. And that works out as 3.31 times 10 to the minus 6 meters is the separation. Now that's all we need to know now, because what we want to know is how many lines there are per millimetre. So if d is the separation between lines, then 1 over d is equal to the number of lines per metre. Okay, because if that's the separation in metres, then 1 metre divided by d is the number of lines per metre, which is 1 over 3.31 times 10 to the minus 6. And that works out to be 3.02 times 10 to the 5 lines per metre. But we are asked how many lines per millimetre, so that means 3.02 times 10 to the 5 divided by 1,000, because it's only 1,000th of a metre, which is 3.02 times 10 to the 2 lines per millimetre, which, three significant figures, is 3.0 times 10 to the 2, which means the answer is C. Question 19 again is a diffraction grating question, so again this is going to be the key equation, and so the first thing we're going to need to do is find the value of d. We've got the number of lines per metre, so 1 over 4.5 times 10 to the 5, 1 over the number of lines per metre is equal to the separation of the lines, which comes to 2.5 times 10 to the minus 6 is equal to d. So we've got that number. Now the idea is then that the maximum angle theta is 90 degrees, because, you know, once, if we think about what's going on here, as you go through the grating, remember what happens is that you get this kind of thing where that's the 0 line, and then you'll get the first order and the second order and so on, and the maximum value of theta, which is the angular separation there or there, is obviously 90 degrees, because you can't have any more than 90 degrees, otherwise you'd be passing back behind the grating. So we know that the maximum value of theta we can get is 90 degrees. So what we do is to work out what n would be if theta is 90 degrees. That's the idea. So we can say that n max times lambda is equal to d is equal to d sine of 90 degrees, which is just equal to d, which is 2.5 times 10 to the minus 6 meters. So we can say that n max is equal to 2.5 times 10 to the minus 6 divided by lambda. And it tells us in the question that lambda is 590 nanometers. So that's 2.5 times 10 to the minus 6 divided by 590 times 10 to the minus 9. Remember, a nanometer is 10 to the minus 9 meters, which comes to 4.24. But obviously the point is that n has to be a whole number, so what that's saying is that when n is 4, that's okay, because that's still less than 90 degree angle, but when n is 5, that's too much. So that means that in practice n max is equal to 4. So the fourth order is the highest order that you're going to see in the diffraction pattern, and therefore the answer is C. In question 20 we're dealing with refractive index, so we're going to use this relationship that the refractive index is equal to C divided by CS. In other words, it's the speed of light in a vacuum divided by the speed of light in the medium. Now remember that in this case we're worrying about the refractive index in air and in the glass that the fibre optic is made of. And remember, in air that the speed is basically the same as the speed in the vacuum, to within as close a margin as we can sort of comfortably ignore. So what that means is that n is therefore equal to the speed in air divided by the speed in the glass, and that's equal to the speed in the air divided by 3/5 times the speed in the air, is what it tells us in the question. Those two terms are going to cancel out, so that's equal to 1 over 3/5, which is 5 over 3, which is 1.67 is the refractive index, and therefore the answer is D.